Welcome to this explainer. We're going to completely deconstruct a massive paradigm shift happening right now. We are moving away from static AI models and stepping into the era of fully dynamic, responsive, cognitive architectures. Because, let's be real, if you've been following the rapid advancements in AI, you already know we're hitting a brick wall with current models when it comes to true, sustained autonomy. So today, we're unpacking the actual structural blueprint required to generate mind-like behavior in both digital and physical systems.
Okay, let's kick things off with a question that seems super simple on the surface, but totally resists a simple answer when you're dealing with complex autonomous systems. What do we actually mean when we say an AI system is responsible? Think about it. Most people will say it means the system is fair, it's transparent, accountable, safe, and yeah, they'd be absolutely right. Those are the foundational pillars of global governance. But the real question is, how does a computational system actually pull that off out in the wild, moment by moment?
And that brings us to a crucial realization. True accountability cannot just be a static checklist that we evaluate retrospectively. It literally has to be an active, continuous process of contextual reasoning. You can't just stamp a model as responsible in a pristine lab environment and then expect it to flawlessly navigate the messy, constantly shifting reality of a live enterprise or, say, a physical factory floor without an encompassing architectural framework holding it together.
So here's our roadmap for today. We'll hit the foundations of cognitive AI, the responsive AI shift, the blank mind protocol, evaluating existing architectures, next-gen enterprise architectures, and finally, robotics and spatial intelligence.
Starting with Part 1, Foundations of Cognitive AI and Why We Are Moving Beyond Stateless Tensors.
Right away, we need to highlight the core gap. An AI model is fundamentally a stateless tensor mapping. It completely lacks structural state persistence and temporal continuity. A true cognitive architecture, on the other hand, operates much more like a unified mind. It integrates perception, memory, and executive control. It formalizes exactly how information is routed through multi-tiered memory structures and attentional filters in continuous real-time cognitive cycles, usually operating at around 10 Hz for executive actions.
To put it bluntly, today's large language models are strictly what we call BIBO systems, bounded input, bounded output. They remain completely passive until you explicitly prompt them. Because of this, they suffer from cognitive stagnation. They just can't maintain active agency without an encompassing architectural framework. Sure, they are incredibly powerful semantic engines, but they lack the decoupled, interacting systems you absolutely need to manage inputs, maintain a continuous state, and actually ground outputs in reality.
Moving to Part 2, the responsive AI shift, moving from compliance to context.
Now the contrast here is pretty stark. Responsible AI, as it's currently practiced by most, treats accountability as a rigid state bound by a static rulebook. Responsive AI, however, treats accountability as an act. It doesn't rely on a fixed set of rules. Instead, its ethics are emergent. They adapt dynamically to the highly specific, real-time features of a given human context. So the governance actually arises from the interaction between the system's reasoning and the exact moment of the encounter. But to prevent context degradation in these highly responsive systems, we have to rely on something called a core invariant. By seeding the short-term working memory with this baseline sense of self, the architecture ensures that even as it processes endless, chaotic data streams, it never loses sight of its foundational directives. It basically establishes this rigid input-output schema so the system avoids hallucinating its core parameters.
Part 3, the blank mind protocol and bootstrapping cognition. To actually enable this dynamic adaptability, and, crucially, to keep the system from getting stuck in these endless deterministic loops, we introduce the Blank Mind Logical Protocol, or BMLP. Think of this as a highly sophisticated logical reset button. When the system detects cognitive stagnation or context corruption, BMLP literally flushes the working memory. It wipes the slate clean and rebuilds the context entirely from primary sensory cues, ensuring the AI stays responsive to emergent scenarios rather than just freezing up in a deadlock. And the fascinating thing is, BMLP operates across all these tiers simultaneously. As a reasoning protocol, it breaks deadlocks. As a cognition protocol, it lets the system boot its sensory processing without relying on preconceived concepts. As a decision protocol, it acts as a fallback policy when faced with contradictory choices. By actively flushing out corrupted context, the system can continuously prioritize which responsible virtue to follow in real time, instance by instance.
Okay, let's trace the exact flow of data through this cognitive processing pipeline, starting with Phase 1.
Raw sensory streams, whether that's LiDAR data in a robot or API payloads in an enterprise app, are ingested. Perception modules then compress all that noise into structured semantic feature tokens. Next, these tokens are merged with active goals in the working memory to build context. Finally, this freshly built situational model acts as a query, triggering a spreading activation that pulls relevant historical patterns straight out of long-term memory.
This visible chain of logic is honestly the ultimate form of transparent accountability. The engine predicts states, the planning module breaks down goals, and the decision module resolves conflicts using utility equations right before it executes an action. You aren't just certifying an outcome after the fact, you are auditing the real-time reasoning itself. Because this entire chain can be examined and challenged step by step, it is vastly superior to any retrospective certification.
And finally, we have Phase 3. The physical or digital actions alter the environment, which generates fresh feedback. The system introspects on its prediction errors and updates the utility scores of its actions. Successful patterns get consolidated into procedural rules. This continuous feedback loop is exactly what makes responsive AI active rather than static. It is constantly learning and adapting its procedural memory in real time.
For this cognitive pipeline to even begin, it needs an injection protocol. It needs a genesis state. This is essentially a foundational vector seeded into working memory that kicks off the continuous active inference loop. It gives the architecture that vital contextual starting point so the whole cognitive cycle can actually boot up.
Part 4. Evaluating existing architectures. A quick comparative analysis.
When we look at the trade-offs of prevailing architectures, we see a really clear divide. Traditional models like ACTR and SOAR offer robust execution, but they struggle with complex scalability. Then you have LLM-based architectures like Koala. They have exceptional semantic depth, making them highly suitable for the enterprise, but they suffer from high latency, meaning extremely low real-time decision-making capabilities. Conversely, robotics architectures like 3T lack that enterprise semantic depth, but they totally excel at microsecond reactive physical control.
That brings us to Part 5, Next-Gen Enterprise Architectures.
In the enterprise, a cognitive architecture relies heavily on knowledge graphs and retrieval-augmented generation to serve as its semantic memory. But the real game changer here is the metacognitive subsystem. When paired with the blank mind protocol, it completely shifts rigid compliance into real-time, context-dependent policy adaptation. The system is continuously evaluating the active task's risk profile and regulatory context, dynamically compiling compliance parameters directly into its procedural rules right before executing an API call.
And finally, Part 6, Robotics and Spatial Intelligence.
The physical world requires a vastly different structural approach. An API taking 2 seconds to resolve is fine. A robotic arm taking 2 seconds to resolve a safety conflict, that's catastrophic. Here, the architecture has to prioritize spatial intelligence using a decoupled active inference loop. You have a slow, deliberative planner sitting at the top, while a high-frequency controller adjusts motor actions in milliseconds at the bottom to ensure physical safety. Meanwhile, the theory of mind module analyzes gaze and physiological signals to interpret human intent in real time.
So the core dichotomy really boils down to this. Enterprise software relies entirely on semantic state, tracking documents, policies, and workflows. Robotics, however, relies on physical, spatial state transitions, navigating geometry, velocity, and multi-sensor fusion. While both utilize that same core pipeline of a cognitive architecture, their physical and digital realities dictate completely different state priorities.
I'll leave you with this thought. The question of whether an AI system is truly responsible cannot be answered in advance by a static test. It can only be answered by examining how the system behaves when it encounters the full, messy complexity of a real human situation. Anything less than a real-time, context-aware cognitive architecture is honestly just paperwork disguised as accountability. Thanks for joining me on this explainer, and I highly encourage you to keep questioning the architectures that are shaping our future.